Hi everyone, welcome to the video lesson for Monday and Tuesday, November 30th and December 1st. So we started our lesson today by thinking about metallic compounds and what properties they would have. So for example, I gave you iron. What are some properties that you know that iron has? So we got a lot of answers like, you can bend it, you can mold it to be a certain shape. That's how we get skyscrapers. It has a really high boiling point. That's why it doesn't melt unless you have it in like a furnace. That it's really dense compared to most things. I got a lot of very different things. It was very good. And then I also asked if you wanted to show off what are two chemical compounds you ate on Thanksgiving. I got some really good ones. Unfortunately, I feel the need to tell everyone turkey, gravy, potatoes are made up of chemical compounds, but are not chemical compounds themselves. Some common ones would be table salt, sodium chloride, glucose, sugar, tryptophan, a type of protein found in the turkey. Those are some of the common ones that I'm sure everyone had a little bit of. And then there were no real homework assignments tonight. Just, keep eating your Thanksgiving leftovers if you're lucky enough to still have any. Mine are almost out. I'm so sad. And we're going to be doing a lab on Thursday and Friday. So if you want to take a quick look-see to see what we're doing, those videos are already up on my YouTube channel. So after our warm-up, we went and got our new copies of our Part 2 notes for Unit 4. So you guys know the drill. Go to the module, click on that student copy of the notes Part 2. It's going to ask you if you want to make a copy of the document in your Google Drive. Click yes. And I always strongly recommend that you keep a copy of it in a Google Chemistry folder. So you should have a folder in your Chemistry Drive just for your chemistry documents. That way, if you get stuck on your homework and you're not sure what to do, all of your chemistry stuff will be in one place. Remember, this is to save you time. This is to give you a version of an abridged textbook. So everything we cover, everything you need will be in these PowerPoints all year long. You might refer to things back in the first unit PowerPoints. So everything you need is right there as a reference. So we're going to start on page 2 of your Google Notes, our first page with words to type in. So this is about the nature of bonds. So bonds are a force that holds my atoms together and makes them function as a unit. Now, you're about the age where you or your friends have started dating, and you might have noticed that when one friend, or maybe you, when you get a romantic partner, they kind of stop functioning as just a single independent person. Because you can never just hang out with that one friend anymore. It's that one friend and their boyfriend and their girlfriend. They now go everywhere as a pair. That's kind of what's happening with these atoms, except it's a little bit more permanent for our atoms. It's a little bit harder to tear those apart. So my atoms now are stuck together. They go everywhere together. They function as a unit. They used to be a sodium and a chlorine. Now it's a sodium and a chloride, and they are stuck together. They are bonded. There are 3 major types of bonds. We're really only going to focus on the first 2, though. We have ionic, covalent, and metallic. And then we've already heard this, but I love to repeat myself. That's why I'm a teacher. I love to repeat myself. Ionic means there's been a transfer of electrons. So here in this image, I have sodium and I have chlorine. Well, now it's chloride. It has a charge. My sodium lost the 1 valence electron that it really didn't want to begin with, let's be honest. And my chlorine really wanted 1 more electron, so it accepted that electron and became chloride. So those electrons were transferred, and now I have a bond. For covalent compounds means that those atoms are cooperating. Covalent cooperates. They share valence electrons, so they both are able to achieve that total of 8. Now, you might have heard ionic compounds referred to as molecules, like a molecule of sodium chloride or a molecule of table salt. That's technically not correct. It's kind of like calling you guys children. It's kind of correct. I mean, you guys are all under 18, so if you're not an adult, you're a child. But you don't like to be referred to as a child, do you? You're a teenager. You're a young adult. So formula unit is the correct term for ionic compounds. But for covalent compounds, that's where we get molecules. So I will have a molecule of water. I'll have a molecule of carbon dioxide. So on our next page, we start talking about covalent bonds. So each atom is going to hold onto its own valence electrons. They become more stable by sharing their valence electrons so that everyone gets their octet. It's kind of like, think back to in school when you had textbook work to do in a class, but your teacher didn't have enough textbooks for everyone to work by themselves, so you'd have to buddy up with another person. You'd share that textbook. Okay, I'm done with number 3. Can I turn the page? No, I'm still working on page number 3. Okay, I'll wait. Neither person has that textbook fully to themselves, but both partners has that textbook enough to get what they need. Everyone gets what they need by sharing. So over here, I have water. Water has single bonds, and a single bond means that one pair of electrons or 2 electrons are being shared. So here is my hydrogen. It has its 1 valence electron. Here's my other hydrogen. It has 1 valence electron. And then I have my oxygen. It has 6. So my oxygen desperately wants 2 more valence electrons. So it's willing to share 2 of its electrons to get 2 more. My hydrogen, remember it only has energy level number 1, so it doesn't get a full 8. It can only hold 2. Finds that oxygen and says, well, I can't solve all your problems, but I've got 1 valence electron to share. I'll share my 1 valence electron if you share one of yours. And it does that again over here with the other hydrogen. And now my hydrogen is sharing 1 and gaining 1, so it has its 2. My hydrogen over here is sharing 1 and getting 1, so it has its 2. So I have a single bond here. And then my oxygen gets to count all of these as its electrons. So everyone is satisfied. Then a double bond means that there's 2 pairs or 4 total. A triple bond means that there's 3 pairs or 6 total. Over here, I've got some carbon dioxide. My oxygen again has 6 valence electrons. My carbon has 4. My carbon desperately wants to find another 4 so it can have its octet. So my carbon is willing to share out each of its 4 valence electrons to gain another 4 to share with it. And right here, this carbon and this oxygen have a total of 4 electrons total being shared. I have 2 valence from my carbon, 2 valence from my oxygen. So I've got 4 total being shared here. And same on this side, 4 total electrons between this carbon and this oxygen. So I've got a double bond here, and I've got a double bond there. So my covalent compounds all have relatively low melting points and boiling points than ionic or metallic compounds. They have the lowest of all of them. Because their melting and boiling points are so low, these are the compounds that are solids, liquids, and gases at room temperature. If you think about water, I always love to go back to water. Water is a great example of a covalent compound. Water tends to be liquid at room temperature, but I can have some ice cubes last in a room for a while actually. And if we all take a nice deep breath, you just breathed in some water vapor, some gaseous water. So my covalent compounds can exist as solid, liquid, or gas at room temperature. All the gases that you breathe in are covalent compounds. If you're in a room and there's a non-covalent gas, I would quickly leave that room. That is not something you want to deal with. And then I know that when we think about boiling water, we think of a very high temperature, 200 degrees Fahrenheit. Chris, why am I mentioning Fahrenheit? This is a science classroom. 100 degrees Celsius, 373 degrees Kelvin. Sounds like a really high temperature, but it's actually considered a low temperature when you compare it to other types of compounds like ionic and metallic compounds. So all of my covalent compounds have relatively low melting and boiling points. And they are poor electrical conductors. Electricity is basically electrons running in a straight line from point A to point B. So in order for electricity to be conducted, it needs to be able to run free. But in my covalent compounds, those electrons aren't going anywhere. They're being held between 2 different atoms. So my electrons can't move freely in my covalent compounds, so most covalent compounds are very poor conductors. Now, any good rule has its exceptions. Graphite are some of the best conductors we have. That's powering a lot of our innovation with cell phones and touchscreens. That's actually carbon bonded with other carbons. So that's completely covalent, but a very good conductor. And then our acids are actually very good conductors when they're dissolved. So as a general rule, my covalent compounds are poor conductors of electricity, but there are a few exceptions. And then my compounds can be brittle or malleable. Some of my covalent compounds, like I'm looking at my Cool Gear plastic glass that I'm always drinking out of. If I were to hit that with a hammer, it would shatter. It's very brittle. But other covalent compounds can be molded. They can be hammered into a shape or bent into a shape. Think about Play-Doh. Play-Doh is a covalent compound, and you can easily mold that. I've got a styrofoam cup. It'll eventually be changed. Its shape will get changed. Some rubber things, you don't actually have to melt it and put it into a mold to get those to change their shape. So it depends. Some of them are brittle, but some of them can be very malleable as well. Some common covalent compounds. We have nitrous oxide, also known as laughing gas. It's used as an anesthetic for your dentist. When you get something done, like having cavities drilled, that's a very painful procedure. If your dentist gives you nitrous oxide to breathe in, it raises your pain tolerance. So it still hurts, but doesn't hurt as much. It's also used in some cars. I believe usually like race cars, it'll give you a good boost to your engine power, makes you go a little bit faster for a little bit. Methane, CH4, is a flammable gas. It's what we use in our Bunsen burners in our classroom. If you have a gas stove in your house, you're probably burning methane gas there. And then I've got a cow. So methane is one of the four most potent, strongest, has one of the biggest effects in global warming. Water is the most strong, then methane, then carbon dioxide. One large source for methane in our atmosphere is actually cows. Cows burp methane gas. So a lot of times people say if you want to help the environment, if you want to help change things for the better, to give up meat. So when we eat more burgers and more steaks, they have to go out and raise more cows to feed us. If we eat less meat, there'll be less cows being raised, and if there are less cows being raised to feed us, then there'll be fewer methane burps. Then we have sugars. Sucrose and glucose are some that we have here. I also have fructose down there in the image. Glucose is what our body uses for energy. It's what our cells use. It's the gasoline that keeps us running. And then we have hydrogen peroxide, H2O2. It can be used to bleach your hair, bleach other things. I wouldn't recommend it. I have seen other people try to bleach their hair and then watched it fall out for over the course of the next week or so. So maybe don't try bleaching. I know we all miss the salon. I miss it too. And it's also used as an antiseptic. So if you get a cut or a scrape, it's common to put some hydrogen peroxide on that cut or scrape to kill the germs, to keep you healthy. However, hydrogen peroxide is very good at killing things, very good at killing those single-celled organisms. So when you pour it on a cut or a scrape, it actually damages some of your skin cells as well, and it can actually make it take a little bit longer to heal. Now, if you don't have Neosporin or some rubbing alcohol, then it's still a good thing to use, just maybe not your first go-to. So in my ionic bonds, my anions and cations are held together by their opposite charges. Remember, there's only 4 attractive forces in the universe. This is all the way back from Unit 2. We have gravity, electromagnetism, strong force, and weak force. So that opposite charge is electromagnetism. It's magnets, opposite charges, north and south, positive, negative. So they're held together very strongly. Now, whenever people talk about salt in chemistry, I always correct you. Are you talking about table salt? In our day-to-day lives, when people say salt, they usually mean sodium chloride, what we use in our food. But any ionic compound can actually be referred to as a salt. We have table salt, sodium chloride. We have reduced or low sodium table salt, which is usually potassium chloride. If you're an athlete, you've probably used Epsom salts at some point. In the winter, we cover our roads in road salt, which is a whole range of different types of salts. So, salt really just refers to ionic compounds. Then I'm repeating myself again about the formula units. So, a molecule is just one water, H2O. So, two H's and one oxygen bound together. But ionic compounds, if I have something like sodium chloride, I'm not saying that I have one sodium and one chlorine. This doesn't really ever exist. You never interact with two ions stuck together. If I have sodium chloride, what I actually have is I have this giant network of sodiums and chlorides repeated over and over and over again. So a representative particle is the smallest form of something, the smallest thing I can break it down to being something and still have it retain its own properties. So remember, an element, the most I can break down an element to is its atoms, because a carbon atom will look different from a nitrogen atom. If I go further than that into the protons and neutrons, well, a carbon proton is indistinguishable from a nitrogen proton. They don't look any different. But my formula unit is as far down as I can get to my ionic compound and still have those same properties. So someone is always gaining, someone is always losing one or more electrons. That's how my bond is formed. Once that transfer has happened, it's happened. No takesies backsies. It's happened, it's done. And they do that so they can get their complete octet, so they can get their complete 8. So down here, I've got my sodium and my chlorine. My sodium wants a complete octet, so it gets rid of that 1 on the outside ring. Chlorine desperately wants just one more electron so it can have its 8. So they make a switch. Now sodium has a positive charge. It lost that third energy level, so its outermost shell has 8. Then my now chloride, because once it has a charge, it's chloride, now has a negative charge and it has its 8 electrons. And these are usually metals combining with my nonmetals. There are some exceptions. Notably, if it starts with NH4, my ammonium, that's still an ionic compound, even though it's starting with nonmetals. So my ionic compounds make crystalline solids, which is this. A crystalline solid is just a regular repeating pattern. This is a 1-to-1 ratio. It's very simple. Red, white, red, white, red, white. It's the same two colors repeating after each other. Each white anion is completely surrounded by red cations on every side, even on the inside. Every red cation is completely surrounded by white anions on every side, even on the inside. They are as close as can be. Every positive charge is completely smothered by negative charges. Every negative charge is completely smothered by positive charges. They're as close as they can be, and they are as efficiently packed as possible, which makes it very rigid. They're very strongly attracted, and I can't move them. If I try to shift all these up by one atom, suddenly I'm going to have positive next to positive, negative next to negative. I can't have that. Those are repulsed by each other. So I can't bend or move this. It's a very rigid structure. This is what makes it very brittle. And it's also going to be a very good insulator or a very poor conductor because for electricity to flow, to be conducted, my electrons have to be able to move. There's no electrons being moved here. They've already transferred. So because they've already moved and all these charges are canceled, there's nothing to do with this for electricity. The electrons can't move around. Now, if I melt this down, go from solid ionic compound to a molten ionic compound, when I go from liquid to solid, I'm still there, I'm still near each other, my molecules are near each other, my ions are near each other, but they're not tied down, they're not in place. So my melted ionic compounds do conduct electricity because now I can see these charges. The charges aren't fully canceled, so I can jump from one ion to the next. Another way I can conduct electricity is if I dissolve this in water. So when I put an ionic compound into water, my water molecules, if you remember back in biology, are polar. They have negative sides and positive sides. So if I have this large negatively charged ion, my positively charged hydrogen sides of water molecules will come, surround it, and carry it off. Then if I have this tiny positively charged cation, the negative oxygen sides of water will come, surround it, and tear it off of the cube. So it'll break apart my ionic solid ion by ion, and then I have ions that flow freely. So water is a very good insulator. Pure water will not conduct electricity. But the water you have at home is not pure. Anything that comes out of your faucet is going to have a little bit of something dissolved in it. It's not normal, it's natural, don't worry. Most of it's fine. Hopefully there's nothing bad in it. But now that these ions are floating freely, they're not canceling each other's charges. So if I try to run some electricity through it, it can easily bounce from ion to ion. My electrons have something to jump onto and travel onto. They can leapfrog it. So dissolved ionic solutions are very good electrical conductors. Now, their melting points are very, very high. Table salt melts at 800 degrees Celsius or almost 1500 degrees Fahrenheit. So that's very high, that's very hot. They're very happy being together, they're very strongly attached. So it's going to take a lot of energy to make them melt and to move away from each other. So, some example ionic compounds we have in our everyday life. We have table salt, sodium chloride. We all know that's used to season food and preserve food. Sodium bicarbonate is another name for baking soda. We use that a lot because it's good at absorbing bad smells in our refrigerators. It's also what gives us lift in our cookies and our cakes. If you make chocolate chip cookies from scratch and you forget your baking soda, you're going to have very flat cookies. You're going to have chocolate chip cookie chips. It's also the main active ingredient in most antacids. So if you ate too much on Thanksgiving, you might have taken a Tums or a Rolaids. That's largely baking soda. It'll counteract the acid in your stomach, which is a great way to segue into sodium hydroxide. So we haven't really worked with acids and bases yet, but most students have heard of acids. And you know that you need to be careful with acid because you can get an acid burn. Well, the opposite of an acid is a base. Sodium hydroxide is a very strong base. Now, in my mind, I think bases are slightly more dangerous than acids. If you get an acid burn, you know right away. But bases can do just as much damage and they can do it very quietly. So bases are very good at dissolving soft tissue like skin cells. This is why we use it in soap. When we want to wash when we're bathing, we typically want to wash off that top layer of skin. So it's a little bit of lye, a little bit of sodium hydroxide, and nice good soaps. It helps dissolve, wash away that top dirty layer of skin, leaving us with nice fresh skin underneath. This is also what's in drain cleaner like Drano. So usually when your pipes are clogged, it's clogged because there's bits of you in there. I know it's kind of gross, but it's true. Hair, skin cells, stuff that you go down the drain gets clogged up. So we pour lye or Drano down the drain, and it will slowly work to dissolve the little pieces of you that were left in there. And then you can just wash it away, wash the goo away. Now, a fun fact, that same chemical, sodium hydroxide, is used in Drano to melt away soft tissue that piles up in your pipes, but it's also used in soap. So when you make soap at home, first off, if you ever do that, be very, very careful because lye is a very dangerous chemical. If you don't believe me, I can show you images of the aftermath of a small lie explosion that occurred at my last school when there was a equipment malfunction. Everyone was safe, don't worry. I was fine because I had my safety goggles on. But when you make soap, you actually have to let it cure for about 3 months. Because if you try to use raw homemade soap right away, it will hurt you. Hence the name of my soap company, Miss Brubaker's Old Fashioned Face Melting Soap. And then lastly here, I've got sodium fluoride. It's one of the active ingredients in toothpaste to help prevent cavities to keep your teeth strong. So now on to metallic bonds. So my metals hold on to those electrons very loosely. Remember, sodium, I use sodium for examples a lot. It has that one valence electron. It wants to get rid of it. So they constantly try to get rid of their electrons. Now imagine a room of metal atoms, a room of sodiums. I don't want this electron, so it tries to give it to the other sodium. Well, that sodium doesn't want that electron. It tries to give it to someone else. That sodium doesn't want it. It gives it to someone else. It's a giant game of hot potato. Usually, when I teach this in class, I start throwing some indoor snowballs at students and say, "You're a metal atom. You don't want that valence electron. Get rid of it." Because none of them want those valence electrons, those poor electrons. Atoms are cruel. No one wants those valence electrons. So, as soon as an metal atom, gets its electron, it throws it away. It gets rid of it, gives it to someone else. Now that it got rid of that valence electron, it has a positive charge. So another electron comes over. It doesn't want that one. It gets rid of it. So these electrons go from one positively charged cation looking for a home, rejected, goes to another, rejected, goes to another, and another, and another. They're constantly moving around. There's nothing to slow them down and nothing to impede them. They just go from one metal to the other metal atom. So they're moving freely. Now, if you don't like the hot potato analogy, the official analogy is that think of cations floating in a sea of electrons. My electrons are free to move around. Now, this is crazy, but if you have anything metal nearby, like I've got my stylus pen right here with some metal, that's what's going on. If I were to zoom all the way in, there is a hive of activity. Those electrons are not being still. They're traveling from one atom to the other atom, trying to find a place to call home, and none of the metal atoms are nice enough to let it stay. So my electrons are constantly moving in a metal. Because the electrons it already has are moving so happily and so freely, this is why metals are such good conductors. They're the only ones that will conduct electricity when solid. Those electrons it already has are moving around. So if I throw in some more electrons into the mix, they will also freely move around and shoot out the other side. So my metals make very good conductors. Now, my metals are also malleable. So when I was a ionic solid, I was very brittle because I can't move. If I try to shift things around, then I suddenly have a positive and a positive, or a negative or a negative. Let me take these two and let's pretend that these are no longer ions. Let's say these are two metal atoms and a metal bond. They both are technically positively charged. They're only near each other because they're kind of sharing all those electrons. So it doesn't really matter if they're side to side like this, or if they get rotated like this, or like this. My metal atoms can slide. It doesn't really matter. They don't want to be pulled apart, but they can slide. It's kind of like when you played Red Rover back during recess, and you'd have a nice long link of friends. I guess I'll use this. You have a nice long link of friends, and then someone tries to break through, but they don't. What happens? It bends. Your entire Red Rover line would bend, but you wouldn't break. That's like a metallic bond. You can slide and you can move. I can slide these and I can move these. I just don't want to break them apart. So that's why metals are so malleable, because those atoms can easily slide. There's nothing holding them in place. They're held together. They got to be near each other. They can't be taken apart, but they can be slid around. As long as you don't move them away from each other, they can rotate. And then my metals are also ductile, which means that they can be drawn into a wire. Now, I thought about it a lot because ducts, wires, I couldn't really make a good connection to help students remember ductile means wires. So what I like to do is I like to think of a copper wire starting in a spool, then going out and then bent into the shape of a beautiful duck. That's my favorite duck from last year, of all the ducks I kept. So it's ductile. It's a copper wire in the shape of a duck. So here is the last slide of our Google Slides. This is a nice summarizer for all the different properties we went over. So for ionic compounds, they tend to be made out of metals and nonmetals. My electrons are transferred. That's how I make their bond. My conductivity, it only conducts electricity if it is dissolved or melted. Their boiling points are very high and they're very brittle. Then my covalent compounds tend to be nonmetals with other nonmetals. My electrons are shared between those atoms. They tend to not be conductive. They do not conduct typically as solids, with the exception of graphite and graphene. And they don't really conduct in water either, unless it's an acid. Acids are a special kind of covalent compound, and they conduct very well in water. Their boiling and melting points are very low compared to the other types of compounds, and they can be brittle and break when hit, or they can be malleable. Both are acceptable. For metallic, I said metal and metal. It's probably a little bit more accurate to just say metal. You tend to have one type of atom for a metallic bond, so a bunch of iron atoms, a bunch of copper ions. Their electrons are being shared. No one wants those electrons. No one wants those valence electrons, so they just kind of share it all together. They're incredibly conductive since those electrons are already moving around willy-nilly. They're able to take on more electrons and let new electrons pass through. They have very high melting and boiling points. There are a few exceptions, a few people pointed out in classes, like mercury will actually be a liquid at room temperature. Gallium is typically considered to be solid at room temperature, but it will melt in your hand. It still has a very low melting point. And then my metallic compounds are malleable, they take on new shapes, and they are ductile. You can draw them out into a wire. So there was no official homework once again tonight. If you want to preview the lab, you're more than welcome to check out the other videos on my YouTube channel. Those are where our lab videos are coming from. And stay safe, guys. Have a good one. Make good choices.